Swayam Prabha. Digital India. Educated India.
Welcome back. We did additions to alkenes with cyclic compounds, the cyclopentene compounds. Then we did trans, and just for completion, we'll do a cis. All right, let's see what we can get with cis alkenes.
Okay.
All right, so let's look at what this cis can do. Cis Z. So this is going to be 1, 2, 3, 1, 2, 3, 4. So you're going to number from here. It's on 3 carbon. It's a Z. So it's a 3Z. 2 methyl. 1, 2, 3, 4, 5, 6, 7. So it's a 2 methyl hep3ene. Let's look at what happens to it with osmium tetroxide. Osmium tetroxide can hang on to that monkey bar below or swing up, get oxidized, and leave 2 hydroxides. So the way to draw this is to draw these as wedges, the ones that are coming down, and draw those as dashes. And these are coming toward you, and these are going away from you. Let's say you can even draw it the other way, but just keep it consistent throughout the whole thing. Don't switch around in the middle, then you get into trouble. And then you can tilt them down when the hydroxyls are up and tilt them up when the hydroxyls are down. That way you have space to draw the hydroxyls. So this is what I mean. Here's your 1, 2, 3 here, and these are pointing down. And the hydrogens are going here, pointing kind of down. And your oxygen then flips up, OH, OH. And you can do the same thing, except this time you're going to put the hydroxyls down, so you want to draw these kind of tilted up. And this is going to be up. And then now you have plenty of space to draw your hydroxyls down. And then if you take a mirror, put it here, you're going to get this exactly reflected on it. So it's an enantiomer 1-to-1 raceme. We did this again with your trans and cyclopentyl and so on. So I'm sure you have a lot of practice. I just want you to pause right now that you've seen how to draw one, turn this off, finish all of these, and then turn it back on to check if your answers are right. All right? Don't just, look at me doing this. You're not going to learn a thing. All right, let's look at what BH3 can do. Well, over here, this is a di-substituted cis alkene. You get an R group and a hydrogen, R group and a hydrogen. The steric bias is not too different. I mean, you have isopropyl versus propyl. So you can go this way and this way. Maybe there may be a little bit more of one or the other, but for the most part, it's going to go both ways. So you can have the hydrogen here, boron here, and blast it off with peroxide into a hydroxyl, or you could have hydrogen here, boron here, and then, oxidize that too with peroxide to an alcohol. So let's draw both of those possibilities. So here you can have one, and these two can go up or down. So here's one where you can have hydroxyl here and hydrogen here. You can have BH attack from below, so your hydroxyl and hydrogen will be below. So then you tilt this up a little bit and leave some space there for your putting your hydroxyl. So this could be a major, one of the major, and this could be your other major. Again, you're going to have your boron and hydrogen now sit in this direction, BH. For this, it was sitting BH. So both are going to be approximately the same. You could think of this having a little bit more steric than this. It's hard to tell. You have to look at the experimental values. So these may be slightly more than this, if that's the case. And here it is. And then tilt your hydrogens up and up. And so now you can put your hydroxyl here and hydrogen here. Again, you're not talking about differentially substituted alkene termini. They both got R groups and hydrogens, so your steric bias is not a whole lot. And this time I'm just doing major products. As you can see, we got quite a few, so I don't really have any space to write the minor products, but it's a good idea for you to look at the previous one where we did the trans and try to come up with minor products that are very similar here for the cis. All right, let's look at chlorine, just chlorine, nothing else. Chloronium ion goes up, chloride attacks here or here, so you can have anti-chloride on both ends. Let's draw it out. So since it's anti, you want to have these tilted in opposite directions because you know you're going to put the chlorides in opposite directions. So chloride down and chloride up. Plus, you want to have the same thing, but now opposite directions, chloride here and here, so tilt this down and tilt that up. And now you're going to put your chloride here and here. So you can see these are mirror images of each other, so they are enantiomers, 1-to-1 raceme. What about these? These obviously, if you put a mirror here, you'll get this. These two are enantiomers. And these two are enantiomers. Great, but what about these two? Or these two? So basically, what's this and this and this and this? What do you think? Are they diastereomers? Are they? Well, there's no chance that they can be meso because you don't have a plane of symmetry. What do you think? The whole thing's connected differently. You have a hydroxyl here on carbon number 3. Here your hydroxyl is on carbon number 4. They're not even in the same place. So therefore, these are connected differently. So they're constitutional isomers. And same here. This one is a constitutional isomer of this. All right, so over here, these are enantiomers, but these are constitutional isomers, and these are constitutional isomers. Let's keep going. Over here, we have chlorine with alcohol or water or some protic solvent. What does it do? It's going to make a chloronium, and then you're going to attack with your protic solvent. Do you have a preference? Well, both of them are equally nucleophilic carbons because you have an R group here and an R group here. So you could have your chloronium then attack up, and your alcohol or water can attack here. Or you could have your water attack here. Let's just do water for this one. So here's your anti-addition. So you're going to have these come on opposite sides. So you want to draw them a little bit kind of staggered there. Your chlorine can be pushed over to this side. Water is going to go over down. And if you want to show your hydrogens, you can. And it might be a good idea to do that, just so that you can check for yourself that they're on the same side. Either they should both be wedges or both be dashes. I mean, if you turn this around, these hydrogens are going to come in front, and your R groups are going to go back. Or you could have had the water attack that chloronium from this end. So they're both going to be major. When you're drawing the other one, whatever was coming down, draw it up. But still, wedge is a wedge, because we're looking at it, in the same perspective. And so chlorine roll over to this side, and hydroxyl comes in here. Or water comes in here and gets deprotonated. These two are actually going to be what? Enantiomers, diastereomers, constitutional isomers, what are they going to be? As you can see, the connectivity is completely different. So these two are going to be constitutional isomers. As you can see, they're not even on the same carbons. All right, is that it, or do we have any more? Well, both cases the chlorine's up, so we have made a chlorine up and attacked with hydroxyl here and here. What if the chlorine's hanging down and you attack with hydroxyl here and here? Let's draw that out. So here we could have a chlorine hanging down and attack here. Let's draw that out. So the chlorine's going to move over and the hydroxyl is going to attack, from the opposite side to push the chlorine over here. Or when the chlorine is hanging down as a chloronium, you can have attack of the water here. Let's draw that out. It could be alcohol, it could be amine. I'm just drawing these two. So over here, you could also have this as a possibility. So your chlorine's going to roll over on this side, while the water attacks from the opposite end here and gets deprotonated. All right, now do we see some relationships, or do we see some relationships? If you take these two, the way we've drawn it is pretty obvious that if you put a mirror right here, they're going to be reflections of each other. It's beyond a doubt that these two are going to be enantiomers. So let's label this A, B, C, D. So A and C are enantiomers. And B and D are also enantiomers. What about A and B? Are they enantiomers or diastereomers? It looks like chlorine and hydroxyl are switched. If you number it correctly, you'd number from this end to give the hydroxyl the lower number. 1, 2, 3, 4 is a hydroxyl, and in this case 4 is a chloride. So they're not even the same compound. They won't have the same name. They're completely different compounds. The only thing common is their molecular formula. So those are constitutional isomers. So A and B and C and D are constitutional isomers. All right, so we have a bunch here, okay, just because of the selectivity or the lack of selectivity in this case, because you can attack both places. Let's look at MCPBA, metachloropurbenzoic acid. That only puts a cap on top or a bottom. So that's all it does. And since it's all going to be happening at the same time, it's going to be a concerted reaction. Concerted reactions don't have any opportunity to spin at random. They are kind of frozen in a particular configuration. So that's attack from up, and you can get attack from below. Again, just tilt these up, but keep the wedges as wedges and keep the dashes as dashes when you're doing these wheel questions. So your oxygen can attack from below. Do we have any other possibilities? Since it's concerted and you have a transition state that gels into this, there's really no chance of, attacking or moving places or rearranging. This is pretty much it. So these are both mirror images of each other. You put a mirror here, you're going to see this. So these are enantiomers, 1-to-1 raceme. All right. Now, what about if you take the epoxide and open it up with a nucleophile in an acid media? Does it really matter whether it's acidic or basic? In both cases here and here, you are going to get a secondary carbocation here and a secondary carbocation here. Not too much difference in the strain. And steric-wise, it's hard to say which one's more by just looking at it. You may have to do some molecular modeling calculations and experimental data here to say which one's going to be more. Is this going to be spinning and whacking out the nucleophile, or is this going to be whacking out the incoming nucleophile? It's hard to tell. So therefore, you're going to have almost a one-to-one. So your nucleophile here, whichever one it is, can attack here or here almost equally. Same here, can attack here and here almost equally. So let's draw that out. So this first step is what you see here. The only difference is this phenyl group is replaced with a methyl, but the peroxy part is the one that does the job. So we got this here. And now after we put the peroxide, we're going to open it up. Let's say we open it up with propanol. So isopropanol here and here. Let's draw that out. Let's say we call this A, B. And let's call this C, D. And so now since we are going to add this anti, one of them is going to go this way, the other one's going to go in the other direction. So therefore, we have to tilt this in a different direction. So if I attack here, these are going to be tilted up. These are going to stay here just because the oxygen is going to roll over and go over to here. And it's going to get protonated after that. And let's say you have some alcohol. Why not propanol? It can attack at B. So then that is going to be, B is now going to be going up and A is going to go down. Hydroxyl moves over. This is still from hydroxyl up, so it's going to stay up. And your alcohol or water or some nucleophile, it could be even hydride. So it could be any alcohol, water, amine, something protic. That's all it is. If you have something protic in an acid media where you protonate this, you're going to open it up here and here. And as I said, it's hard to tell which one's going to be more because there isn't much of a difference between the steric and electronic bias. Yes. All right, let's look at this. C is going to have the nucleophile attack here, and D is going to have the nucleophile attack here. So if you attack here, this is going to roll over, and so this is going to go down or tilted down, and this will be tilted up. And you would have your oxygen here and your nucleophile. I'm just putting a propyl group, it could be anything. Same thing here, D comes in over here. And so this is going to then tilt down to make room for D. And that's going to be tilting up. All right, now, I'm going to ask which was the relationship. Well, let's look at it. Here on this carbon here, you have an ether, and on the same carbon as here, you have a hydroxyl. They're not even the same thing. They're not linked the same. So that's going to make it a constitutional isomer. So A and B are constitutional isomers. Let's look at C and D here. Same thing as before. This has got an ether group on this carbon, and at the very same place in that molecule, it's got a hydroxyl. So C and D are also constitutional isomers. Well, what about A and C? A and C, if I put a mirror right here, it's going to reflect this. A and C are going to be enantiomers, mirror images. And B and D are going to be enantiomers. You can see they are reflections of each other, B and D, enantiomers. But what about A and D? Well, you can see A and D are going to be different completely in terms of connectivity. Therefore, A and D are also going to be constitutional isomers. What about C and B? Well, same thing. You can see they are also going to be connected differently. So C and B are also constitutional isomers. So A and D, A and B, C and B, or B and C and D are constitutional isomers. A can only have one mirror image, that's C. B can only have one mirror image, and that's D. And those are enantiomers. So you have a mixture here. So when you have a alkene here that's really doesn't have a differentiation in steric or strain between the two termini, you can get a lot more mixtures. For example, if we had put an R group here, then you would only get nucleophilic attack there. That would be regioselective. So the regioselectivity here is lost just because both the regions here are termini have pretty much the same amount of steric and stability, electronic stability. All right, let's move on over here. MCPBA, anionic nucleophile. That means a negative anion attacks your epoxide. Again, you can attack the epoxide here or here, here or here. And let's draw all of them out and see if there is a difference. Let's choose, let's say, a sulfide to open it up and see what happens. So you have A, B, C, and D. So it's pretty much going to look like this, except instead of an oxygen, you're going to get a sulfur. All right. So if you want to watch me do it, we can do it. Or you can just fast forward and move on to the next one. Here's your epoxide getting hammered by a sulfide over here. So your nucleophile is going to be, let's say, R, S, and A. And so let's say your R group is going to be let's do something different. Isobutyl. Let's see, and you're going to roll over the oxygen and then protonate it, and you're going to get an OH here. So this is pretty much the same story as this. As you can see, there is really no selectivity between the termini here. And so your nucleophile can attack here and here, about the same. There may be slight differences, and unless you do the experiment, it's hard to tell. So, you know, it's about the same for both. One's an isopropyl and one's a propyl. And here is your hydrogen, and your hydrogen. These are wedges. And again, you're going to have your RS attack here. So your sulfur is going to be here, which is going to roll over that oxygen over to the other side. And you're going to have sulfur with the same isobutyl group. That's at B. Then you can attack at C and roll over the oxygen below. So you can have the same, pretty much the same thing here. And you can have your sulfur, as I said, attack at C. So your sulfur is going to form a bond with that carbon, and your hydroxyl rolls over here. Or you could have attack at D with the sulfur. And it's very similar to what you have over here. So your sulfur is attacking here and rolls over the oxygen to the other side. So here is your sulfur and your hydroxyl. So you can see you can get 4 different products. Relationship is pretty much like this. A and C and B and D are going to be enantiomers. And then AB and CD are going to be constitutional isomers. Do we have any more constitutional isomers? Let's take B here, B and A. We already said A and B. B and C would be constitutional isomers. B and C and A and D would be constitutional isomers as well. So we got a whole bunch of constitutional isomers and enantiomers all mixed up here. It's a mess. So this is one reason why it's nice to have some kind of selectivity, but if you don't have any definite regioselectivity, you can get a lot of mixtures. All right, let's look at AgOAC and water. Let's look at mercury, mercuric acetate. What does that do? Mercury can form a three-membered ring here, and you can attack with the water below here or here. Mercury can make a three-membered ring here, and you can attack here and here. So again, 4 different products. Let's look at the relationship. All right, so in this case, since your second step is adding a hydrogen, you are going to have an achiral center at one of the termini. If the hydride adds here, this will become achiral. If the hydride adds here, that would become achiral. So you only have one chiral center. But let me draw it out just like before, just to show you. So over here, let's say your mercury is going to go and your water attacks from the bottom here and gets deprotonated. You're going to put a hydrogen here, 2 hydrogens here. So this is not going to be a chiral center. So really we don't have to draw wedges and dashes for this carbon. It would be the same here if you have the mercury down and hydroxyl attacking from above. So let's draw that out as well. So mercury is, let's say, going to be hanging down, and your hydroxyl is going to then attack that. OH goes up, and then your mercury will be hanging down here and getting displaced by the sodium borohydride. So now you're going to have a hydrogen there and a hydrogen coming in, and so now that's achiral. So you only have really one chiral center here, which is this carbon. Well, what about if your mercury is here and your nucleophile comes in here? So if your nucleophile comes in here, it can come in from the top or bottom. Let's draw that out. And the hydride would go here. So this would become achiral, this carbon, and this carbon would become chiral. So you can either have that go up and your hydroxyl attack here, or it can go down and your hydroxyl can attack from above. So both times you are going to get a chiral center here. And these are going to be hydrogens here. So this, since we have 2 hydrogens at this carbon, that's an achiral carbon. So you only have one chiral center here. All right, let's look at relationships. A, B, C, D. Let's look at it. A and B, what's the relationship? You can see if I put a mirror, it's going to reflect on that, just like the way it is. So here's only one chiral center. A and B are enantiomers. What about C and D? Again, mirror image. C and D are enantiomers. What about A and C? Do they even have any kind of relationship? Not really. Here your hydroxyls on carbon 3, and here your hydroxyls on carbon 4. So they're a completely different name and structure. So they're just constitutional isomers. AC and AD are constitutional isomers. BC and BD are also constitutional isomers. I'm going to write that over here. All right, let's look at the next one. HX addition. What's HX going to give you? well, let's at least draw the intermediate for this. So the intermediate is just the hydrogen protonating this and giving you a carbocation. It can give you a carbocation either here or here. But let's say the carbocation's here. What do you think is going to happen to this? If you put your hydrogen right here like this, what would happen to your carbocation here? Right, whenever you have Markovnikov, remember you got to look at possibilities for rearrangement, except if you have mercuric acetate, that prevents rearrangement. So now you have a secondary, that ain't too good. So you can have a hydride shift. Your hydrogen rolls over house, moves over, just to make that molecule happy and more stable. So now your hydrogen is here. I'm going to put this in a different color so you can see that, and you put a positive right here. All the action is going to be on that positive. So you have a chloride. At least at low temperature, we can assume there's going to be way more SN1 than E1. So I'm just going to draw a major, and chloride or bromide or iodide is going to attack from above and below. Does it really matter whether it's going to be up or down? Look at this. It's got two identical groups on it, so it's going to be achiral no matter what. So here's a tertiary carbocation, and you know that's the most stable here. So tertiary carbocation can then be attacked by a nucleophile. The nucleophiles here could be iodide, bromide, or chloride. I mean, let's do iodide just for this one. And we only put one of these at a time. And so you can have attack above or below, either way. So that's the main product. Yeah, there may be lots of other side products. For example, attack here, attack here from opening it up in the other direction, rearrangements, lots of possibilities. But when you get to a tertiary carbocation, you know that's the most stable, so that's the major product. Let's look at sulfuric acid. Same deal as this, very similar. You'll have a proton here, ripping this off, and let's say it ripped it off in this direction, and you're getting a tertiary carbocation just like here. You can have protonation with the sulfuric acid this way or here or here. Let's say you put this over here, then you'll get a secondary carbocation. Well, no grief there, because this hydrogen can move over and create a tertiary center just like below. So, I mean, this is just a repeat of what happened. And so you would have your carbocation here, and, well, this can be attacked by water. Sulfate is not, or HSO4 minus is not a good nucleophile. So water is the one that's going to go and attack that, and you will get OH there after deprotonation. Is there anything else that can happen? Typically with sulfuric acid and water, if you heat these up, you are also going to get elimination. So you would get elimination here with the tertiary, with this hydrogen leaving and making a pi bond there. So you could have both those products here. So you could have an elimination where you would have a double bond right there, and water acting as your weak nucleophile. Or you could have protonation, or you could have attack of water at the tertiary carbocation, deprotonation following that subsequently to give you an OH. So both these are possible, and depends on the temperature, which would be the more favored. Heat would favor elimination over substitution. For the most part, though, substitution happens a lot faster, and so substitution products seem to be found in higher amounts. Let's look at hydrogenation, platinum. Sometimes you can have palladium carbon, platinum, nickel, lots of big elements, metals, then, you know, absorbing hydrogen and delivering. And here, they're going to deliver right here. And if it goes on the same side, you are going to get hydrogen on both sides of this, on the same side here. And, well, you're not making any chiral center, so it's really is not a big deal. But it's a syn addition. If you had deuterium instead of hydrogen, then you would see that you would create 2 chiral centers, and that would give you a syn. Now, let's take ozonolysis. Ozonolysis is going to rip this in two, and if you rip that in two, you are going to get an oxygen going right in between. So the way to do this is cut this with a knife, put an oxygen here and an oxygen here. That's all you're doing. And here too, on the other side, you would have this. No change to the carbon framework. KMnO4 cold. Well, KMnO4 cold acts very much like osmium tetroxide. So you would get the same thing, syn and anti. KMnO4 hot would go to carboxylic acids on both sides. So let's do KMnO4 cold. We'll just do the same thing over here. And let's draw this a little bit differently for the enantiomer. So put the mirror right in front. So then these wedges are going to become dashes, and your dashes are going to become wedges, which is your hydrogens. So your hydrogens are coming out, and these R groups are going in, and your hydroxyl is going to be on the same side. So this is a mirror image with the mirror up. This is a mirror image with a mirror on the side. These are enantiomers. There's going to be a 1-to-1. It is not stereoselective. It is syn stereospecific. And it's not regioselective because you have only 2 hydroxyls for both ends. Now I'm just going to put a note to say that with hot KMnO4, you are going to get this getting oxidized to a carboxylic acid, and this side is also going to get oxidized to a carboxylic acid. So that's going to be a 4-carbon fragment. All right, so did we finish all that we intended to do? Did we complete our little cycle here? Yes, we did. And I just want to mention these are the major products, and there are minor products possible for almost all of these reactions. If you have a regioisomer, you can get the other regioisomer as your minor product. Or you can have other elimination, substitution products happening as side products. All right, guys, we will come back and do some synthesis. Hold on tight. We'll see you soon. Bye.